Hello. We are going to work on the practice problems from Module 7. I want you to check your answers before coming to take the test. If you have any questions on the practice problems, please let me know soon, and so that we can get you straightened out before the test on Tuesday. There are some additional practice problems in the back of your book that are good if you're not perfectly clear on how to do it. Okay, so with the practice problems, we know that our constants are, the gravitational constant is always going to be 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So we'll just keep that in mind. So problem 1 says that an airplane pilot nosedives and then pulls his 455 kilogram plane upwards, forming a semicircle in the air. If the radius of the semicircle is 112.2 meters, and the airplane's speed is a constant 73.3 meters per second, what is the centripetal force on the plane? So we're going to use the formula. Centripetal force equals mass times velocity squared over the radius. So this is a straight plug and chug. We know the mass, we know the velocity, we know the radius. So we're just going to put those numbers in. 455 kilograms times the velocity squared over the radius. We checked that all our units were what we wanted them to be, and we get an answer of 2.18 times 10 to the 4th newtons. Okay, problem number 2 says that a popular amusement park ride is made of a hollow cylinder that spins. People stand against the outside wall of the cylinder, and while it's spinning at its fastest speed, the floor falls away. Hopefully we'll get to do this at Hershey Park and we'll be able to calculate. The people do not fall through the hole because they are stuck to the wall of the cylinder. This is because the cylinder's walls are pushing against the people, exerting a centripetal force on them. If the walls weren't there, the people would fly out in a straight line in a tangent to the circle. The friction that keeps them there is created by the wall pressing against them and holds them up and keeps them from falling, despite the fact that there is no floor for them to stand on. If such a ride has a radius of 5.1 meters and spins with a speed of 15.1 meters per second, how much is the centripetal acceleration are the riders experiencing? So the formula for centripetal acceleration is the velocity squared over the radius. We have radius, we have velocity, so we can just put these numbers in. And we get 44.7, and we know the units are meters per second squared. Hopefully this is all making sense to you. I'm going to just keep on going. So number 3 says that a child attaches a 34.5, I'm just going to change it right away to meters, centimeter string to a 15-gram ball. So in kilograms it's 0.015, begins twirling it around his head. He twirls it faster and faster, and when the ball reaches a speed of 12.1 meters per second, the string breaks. So what is the maximum tension the string can withstand? So we know that the force of tension is the same thing as this force of centripetal motion, and we know the formula for that is centripetal motion equals mass times velocity squared times the radius. And so we know the mass, we know the radius, and we know the velocity. So again, a straight plug and chug, as long as we've converted our units so that they are what we're looking for. And we find that the force will be equal to 6.4 newtons. So problem number 4 is going to be a car traveling down a slippery road like today. The mu on the road is 0.22. Remember that that doesn't have any units because it's a ratio between the two surfaces. It says, what is the maximum speed that the car can go taking a flat curve whose radius is 13.4 meters? So we know the couple formulas. We have to think back to the last chapter. We know that the force of friction is equal to mu times the normal force. And when we're talking about centripetal motion, we know that the normal force is going to be the mass times the acceleration. So it's the opposite of gravity, so mass times acceleration. We know the acceleration of gravity is 9.81 meters per second. We don't know the mass in this case, so we'll have to just use that as a variable. We know that they're going to be, so we know that we can put in mass times acceleration here in this formula to figure out the force of friction. So we know that the mu is 0.22, and we know that the normal force is equal to mass times 9.81 meters per second squared. We don't know the mass, but we can just put the word mass in there for now to figure out what it is. And so solving for this, we find that the frictional force is equal to 2.16 meters per second squared times the mass. So then if we go to our other formula that we know that since the car is making a turn, the force of friction is going to be equal to the centripetal force. And so that we can say that that is equal to the mass times the velocity squared over the radius. And if we know that the frictional force, which is now also the force of this centripetal motion, was 2.16 meters per second squared times mass, we have to keep the mass unit in there, and that equals mass, since we still don't know what it is, times the velocity, which is what we're solving for, over the radius. So we see here that mass conveniently cancels out, so we don't have to worry about that. And we can multiply this by 13.4 and then take the square root of it to solve for velocity. And we find that the velocity is 5.4 meters per second, which is the fastest that we can take this turn with the road conditions the way they are. And that is a little bit more than 10 miles an hour, so you have to be going very, very slow on these slippery roads. So this one took a little more thinking through how to do it because we don't know the mass, but we did that substituting like we did on the tension when we hung things with two tensions and kept our variable in there. So hopefully this isn't too upsetting for you. You can figure out how to do this. If not, rewind it and work through the problem again to make sure that you're comfortable with it. So problem number 5 talks about a child watching his toy train moving around a circular track. He finds that the train makes 10 trips every minute. So we know that a minute is 60 seconds. And so he wants to know what is the train's frequency and what is the train's period. So we've already set it up to solve for frequency. Frequency is the number of trips per second. So that's what this is. So we can just solve 1.667 hertz. Trips per second is hertz. And that's the frequency. And we also remember that frequency is 1 over the period. Or we can reverse it and we can say the period is 1 over the frequency. And so we can put 1 over 1.67 and we come up with about 6 hertz as the period. And of course that's not hertz, that's seconds. Sorry. So 1 over seconds is which hertz is, will give us seconds. Number 6 says 2 objects. Object 1 has a mass of 15 kilograms. Object 2 has a mass of 25 kilograms. And they are 45 centimeters apart. I'm going to change that to meters right away. And they want to know what is the gravitational attraction between the two of them. And so we have our formula for gravitation. Gravitational constant times the mass of 1, mass of 2, divided by the distance squared. I always forget to square that distance, so I'll try to remind you to do it as well. So as to straight plug and chug, we know that G is 6.67 times 10 to the 11th Newton meters squared per kilogram squared. Am I going to have to know G on the test, you ask? Of course you are. And we put in our masses, 15 kilograms times 25 kilograms divided by 0.45 meters squared. And we do the math and we find out that the force of gravity between these two objects is 1.24 times 10 to the negative 7th newtons. So remember that when you're talking about the force of gravity between two objects, the masses are important, but even more important is the distance between them. Because that is squared, that's going to really affect the force of gravity. So, problem number 7. How long does it take Saturn to make one orbit around the Sun? We know that the mass of the Sun is equal to 2 times 10 to the 30th kilograms. And we know that the radius of Saturn is going to be equal to 1.4 times 10 to the 12th meters. Hopefully you can see that. And so what else do we know? We know that we're talking about circular motion. So in this instance, we can say the force of gravity is going to be equal to the force of centripetal, the centripetal force. And so we can say that the force of gravity that we know is mass times velocity squared over radius can be equal to our centripetal I did that backwards, of course. This is centripetal force, and this is gravitational force. And so if we set those two things equal to each other, we can do a few things. We can cross out one of these r's, and we can cross out one of these masses. And so we are left with the velocity squared is equal to the gravitational constant times the mass that is left. And so we can now put in our numbers. We know that the gravitational constant, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, and times the mass of the sun, 2 times 10 to the 30th kilograms. And we're going to want to take the square root of that whole thing to figure out Saturn's velocity. So the velocity of Saturn orbiting is going to be 9,761.4 meters per second. That's how fast Saturn is orbiting the Sun. But that's not, of course, what they asked for. They wanted to know how long does it take Saturn to go around the Sun, traveling at 9,761.4 meters per second. So now we're going to think about back to where we had our rate times time equals the circumference equals 2 pi r. So we're going to have velocity times time is going to equal 2 pi r. So we have to remember to use our circumference because it's traveling in an elliptical orbit, which is nearly close to circular, so we count it as circular motion. So we know that the velocity is 9,761.4 meters per second. And we don't know the time, that's what we're trying to figure out. And we know that the radius, they gave us Saturn's radius, was 1.4 times 10 to the 12th meters times 2 times pi. So we want to multiply those together, divide it by the velocity, and we know that the time it takes Saturn to go around the Sun is 9 times 10 to the 8th seconds, which doesn't sound like something very useful. So of course we're going to want to change it into years. And so changing those units into years, we know there's 3,600 seconds in every hour. We know that there are 24 hours in a day. And we know there's 365 days in a year. So using that information, we can calculate that the time is 28.5 years for Saturn to travel one orbit around the Sun. Hopefully that made sense to you, how we got from figuring out its velocity and then plugging that velocity into this formula to figure out our time. So we'll go on to number 8. And number 8 is another orbital problem. It says the orbital period of Io one of Jupiter's moons is 1.53 times 10 to the 5th seconds. He already converted it to seconds for us. I may not be that nice. I may give you days and ask you to convert it to seconds. And if Io orbits Jupiter at a radius of 4.22 times 10 to the 8th meters, what is the mass of Jupiter? Okay, so what do we know? We know the period, we know the rate, and we're trying to figure out the mass. So again, we're going to go to our velocity times time equals 2 pi r. We're going to start there in order to figure out how fast it's moving, and then we can plug it into our gravitational constant formula to calculate the mass. So kind of the reverse of the problem that we just did. So we know that we're trying to solve for velocity here. So it's velocity times 1.53 times 10 to the 5th seconds equals 2 times 3.14 times 4, 22 times 10 to the 8th meters. And so we solve that and we figure out that the velocity of Io is 17,667.7 meters per second. So it is traveling very, very quickly. So now we can take the velocity and we can plug that into our formula of if we're setting this the mass times the velocity squared over the radius, since again Fc equals Fg times gravitational, and we cancel that, and we cancel that, and so again deriving that. The radius. Sorry, I erased both radiuses. Okay, and so we're plugging in the velocity. We want to solve for the mass, so we're going to put our radius over here, and we'll divide it by the big G to solve for our mass. Hopefully you followed what I did there. Rearranging the problem to solve for mass instead of for velocity. So putting these in, we know the radius, 4.22 times 10 to the 8th, times the velocity, which we calculated right here, 17,600. And remember that we want to square that. And all of that divided by this tiny gravitational constant. And we end up with 1.97 times 10 to the 27th kilograms for the mass of Jupiter. Okay, almost in the home stretch here. So problem number 9, we have a satellite orbiting the Earth, and we know the mass of Earth equals 5.98 times 10 to the 24th kilograms. And it has a speed of 1,123 meters per second, and it wants to know what is the orbital radius. So this is kind of the opposite of the problem we did before. So I'm not going to sorry about that. I am not going to derive the equation again. Hopefully you've gotten the hang of that the gravitational constant times the mass divided by the radius will equal the velocity squared. If you don't know how I got that, please rewind it a couple problems and figure out how I derived that. Setting the centripetal force equal to the gravitational force. Okay, so I know that G is 6.67 times 10 to the negative 11th Newton meter squared kilogram squared times the mass, 5.98, 10 to the 24th kilograms, and all of that divided by the radius, which we don't know, and equal to the square of the velocity. Remember to square it. And we find that if we swap these two and do the math, it comes out to 3.16 times 10 to the 8th meters, and that is the orbital distance. And finally, problem number 10 says that a satellite orbits the Earth at an altitude, and I'm going to write it as the altitude, you'll see why in a minute, of 2,314 kilometers. So I'm going to change that to meters. And what is the satellite's orbital period is what they want us to solve for. The radius of the Earth is equal to 6.38 times 10 to the 6 meters. And the mass of the Earth is equal to 5.98 times 10 to the 24th kilograms. That sound you hear in the background is my children beating on each other. We will ignore them. So I wrote down the altitude because we know that that is how far it's orbiting above the surface of the Earth. And we talked about before, if you have something and you want to figure the R, it needs to be from the center of the object to the center of the other object. So in order to find the R between these two, we're going to have to add them together. And so we find that the R equals 8.69 times 10 to the 6th meters. So always keep in mind you're looking at the center of the objects for each other. And so we go back. So now that we know the R, we want to know what the centripetal force is. And we know that that is the mass times the velocity squared over the radius. And again, we can set that equal to the force of gravity. And that will cancel that, cancel a mass. Okay, and so we end up solving for velocity will equal the square root of 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared times the mass of the Earth, which is 5.98 times 10 to the 24th kilograms, divided by the R that we calculated, 8.69 times 10 to the 6th meters. And doing all that, we find that the velocity of the satellite is 6,775 meters per second. Of course, that's not what they asked us for. They wanted us to find the time that it takes. Sorry, swinging you around. And so we go back to the other formula, 2 pi r equals velocity times time. So we know 2, we know pi, and we know the radius. We calculated that by adding all those things together. And we know the velocity. And we're trying to find the time. So we multiply those together, divide them by the velocity, and we find out that the time is 8,055 seconds. And of course we want to convert that into a number that means something to us. 3,600 seconds in an hour. And so we find out that the satellite orbits at 2.23 hours. I hope these all made sense to you. And if not, please wiki me, call me, email me, something. Work on the extra practice problems, and I will see you all on Tuesday. Have a good snow day.